You talked about the Wahlberg effect. What causes that?
The cancer community used to think that the main driver for cancer was genetic mutations. But there's an emerging perspective that changes in metabolism, changes in the way electrons flow through this energetic circuitry through the mitochondria can actually drive the instance of a new cancer cell. And then when a cell becomes cancerous, ditches its mitochondria, it goes back to this selfish state, and then it makes can actually drive the instance of a new cancer cell. And then when a cell becomes cancerous, ditches its mitochondria, it goes back to this selfish state, and then it makes more of itself.
And it tries not to die. Explain that part to me, because I was reading about how cancer cells try and evade death.
Yeah, the best way to think about this, I think, is as a social collective, right? Every cell in this organism cares about the same thing, which is preserving the life and the health of the whole being, right? So every cell in this body is in a social contract with every other cell, right? A cancer cell basically gets out of this agreement and says, no, I'm going to fare for myself. I'm going to take all the energy I can, and I'm going to make more of myself, and it goes into bacterial mode. That happens sometimes because of mutations, and it seems like there are other causes of this. Like, for example, hyperglycemia.
What's that?
High blood glucose, right? Diabetes is a major risk factor for developing cancer. Why is that? I don't think there are good explanations out there based on like the molecular framework of disease and the genetic mutation perspective. If you look with every other cell, right? A cancer cell basically gets out of this agreement and says, no, I'm going to fare for myself. I'm going to take all the energy I can, and I'm going to make more of myself, and it goes into bacterial mode. That happens sometimes because of mutations, and it seems like there are other causes of this. Like, for example, hyperglycemia.
What's that?
High blood glucose, right? Diabetes is a major risk factor for developing cancer. Why is that? I don't think there are good explanations out there based on like the molecular framework of disease and the genetic mutation perspective. If you look at cancer from an energetic perspective, and it's, I think, likely that the increase in blood glucose increases the pressure, right? There's more electrons that are being pushed onto those cells, or to those mitochondria. And when you push too much energy on a system that doesn't need energy, it's like you're trying to shove, a lot of water through a very small pipe.
Something goes wrong.
Yeah, something goes wrong. Something can break. So the resistance is if you push a lot of energy into a very small, container, or into a channel that can support that, then what happens kind of physically is an increase in the resistance to the flow. And then that can lead to the cell trying to protect itself. That's what insulin resistance is in diabetes, right? Insulin resistance is a protection mechanism. There's too much glucose being pushed onto the cell, right? And so that causes this excess, energy coming in. The cell says, too much, and it damages the mitochondria, this excess resistance, because there's too much heat produced, reactive oxygen species, oxidative stress.
I was thinking about smoking, and how smoking also is carcinogenic, it's cancer causing.
Yeah. And
through the lens of the mitochondria, how could something like smoking be cancer causing?
Yeah. It's clear that in cigarette smoke, there are carcinogens. There are molecules that can damage the genome and cause mutations. There's a strong link between lung cancer and smoking, but for all of the other cancers, there's much less of a clear connection between exposure and cancer. Right, the cancers that affect and kill most people, we don't really know, why they come, when they come, and it's clear that there's kind of a long history. And the science behind connecting metabolism and cancer shows that obesity and high blood glucose and diabetes, especially, which causes very high excursion, very high spikes in blood glucose, those things are damaging to our cells. And what the energy resistance principle says is that biology processes energy in terms of resistance. And it makes that kind of computation. How much energy is flowing now, and then how much energy demand and how much energy pressure am I exposed to? And if there's an imbalance, then that causes damage.
Rather than being innocent bystanders, mitochondria are hijacked by cancer. The tumor reprograms them to stop acting like the body's protective energy factories and starts using them as a manufacturing plant to build more cancer cells. Because of this, targeting mitochondrial metabolism has become a major promising frontier in developing new cancer therapies.
Mm-hmm.
It hijacks the mitochondria and uses them to produce more cancer cells.
Mm-hmm. So a normal cell is driven, its behavior, it's driven by the mitochondria. It's like mitochondria are in the driver's seat, right? Mitochondria can basically call the shots. Is the cell to live and divide, right? Or is the cell to contract and remain this kind of cell? Or if it's a stem cell, is it to divide or remain a stem cell? Or is it to die? Right? And cells have to make these decisions all the time. And cell suicide for the greater good is something that happens all the time in our bodies. And that's why and how we get rid of most cancer cells, right? As far as we understand, you have a cell that kind of defects from the social collective, and then the organism has the wisdom to say, okay, this is no longer ours, let's get rid of it, right? Because it could become cancer. And most of the time that works well. But what cancer cells can do is say, okay, they ditch their mitochondria, and then they start to use them for their own growth. And by ditching their mitochondria, they basically immunize themselves against the death that mitochondria could trigger. So mitochondria have a veto on cell life or death, and cancer somehow is able to kind of get away from that.
And it's weird to think about because, the things that cause cancer or that have a correlation to cancer are things like, as you said, like having too much of this stuff here, too much sugar.
The white stuff, yes.
High blood glucose levels, etc., are linked to cancer. And one would wonder why eating sugar in excess is going to increase my probability of cancer. But obviously it points to the fact that it must be doing something to my energy systems, which are causing some kind of malfunction somewhere.
Yeah. And what the energy resistance principle allows us to understand is why that is and what's really happening. If you overload your body with excess energy, the body has to deal with this. And in a simple electrical circuit, if you jacked up the voltage and the system is too weak to take this, then resistance goes through the roof, the transistors start to melt, and then the system, gets damaged. The same thing happens, in the body. If you overload the system with too much energy, too many electrons, right? Very direct parallel with the electrical circuit. There are electrons stuck here on these little glucose molecules. If you ingest this, now it increases the voltage in the body. And then if the mitochondria can't keep up, and because they're not flowing energy because you're sedentary, you're not moving, then that increases the resistance, right? And
they might die or malfunction.
Correct. Or things get damaged, right? The clear connection here is too much energy, increased energy resistance. So then the electrons that normally flow smoothly in your metabolism, right, from the food to your mitochondria, then that whole circuit becomes more resistive. And if you're an electron and you're trying to go through the metabolic pathways looking for oxygen in a mitochondrion, but then at every point in this cascade you face resistance, there's more chance that electron kind of jets out and then becomes oxidative stress.
Well, then what's going on with aging? I've got two women in front of me, and they have two different colors of hair. Now, let's just pretend, for argument's sake and for the sake of this explanation, that this is someone's hair that's gone grey because of stress. And this is what she used to look like, or he used to look like in terms of the colour of their hair. What I found really interesting, because it kind of speaks to lots of things that are going on in the body, is you're saying you can actually reverse grey hair without dyeing it. And if so, what does that tell us about what grey hair is, but more broadly about stress, energy, mitochondria, and everything in between?
Yeah. What we discovered is that hair graying is reversible. And that was surprising, because what I've learned and what most people learn is that when you age, it's kind of this linear progressive decline, and there's kind of nothing you can do about it. But it turns out that if you look on most people's head, you can see things like this. This is obviously, this was dyed, and all of the hairs were white, and then all the hairs are or dark. And if you take a hair like this, the tip here, right, was inside the body long time ago. This is almost like if you looked at tree rings, right? You take a tree and you cut it in cross section, you see like the rings, and then you can say, ooh, this ring was 30 years ago, right? And this ring is today. So you can use that to kind of map the history of what happened in the environment of the tree. You can do the same thing. We all walk around with biological history crystallized in this hair. And that's why if you want to know if someone had a drug, for example, like a month ago or 6 months ago or like 2 years ago, depending how long the hair is, you can actually use the hair and all along would be, the chemical signature of what you took. So you can find marijuana in the hair, here, but not here. So if you have marijuana 6 months ago, it's going to be in your hair and you're going to walk around with that trace, that physical trace in your body.
I need to get a haircut. I'm joking.
And the idea was if we could find hairs on someone's head that the tip was dark, right? And then when you look closer to the body, it becomes white, right? And you would say the hair was young, it was young, it was young, it was young, and then boom, it became old, right? It lost color. Hair graying is a classic hallmark of aging. Then we thought, then you would know that something was happening in this hair follicle, in this person's body, right? That made this young hair become old. And then maybe we could understand the mechanisms of the aging process. So this became a kind of an interesting scenario. And through doing this, we found people started to send us hair samples in Ziploc bags, over the mail. And we were looking for 2 colored hairs, a single hair that has 2 colors, kind of like this. And we found hairs that, head hair, beard hair, pubic hairs that showed the signature. The hair was dark and then it became white, or the hair was white and it became dark again. So we had physical evidence from like multiple people that showed white hairs can go back to being dark. And this contradicted this idea that, aging is this linear progressive process that we're kind of doomed to experience without any flexibility. I was one of the participants in that study. I ended up finding 5 hairs that had this pattern. And when we looked at when the reversal happened, we found that the reversal happened when I went on vacation. And I would go back in those days on annual cycling training camps. So I would go for a week where all you do is you bike, you eat, you sleep. Energy started to move very differently in my body during that time. And then when we looked at the hair and we analyzed the composition, the molecular composition, that's what scientists do. You can take a hair like this, snip the pieces, the white segment, the dark segment. It's all the same genome, right? Every hair has the same genome, the same genetic material, same food, same physical activity, same everything. Why some hairs are like this or like that?